Welcome to the Amateur Radio Technician Online Licensing class. This is session 3 by David Okren, W7DAO. We're going to start with propagation tonight, and as always, we're going to go a little bit deeper in some of the areas than the book does. But remember, you're only responsible for what the book covers with regards to the test. And as always, just read the book, do the questions, and then go in the back of the book and keep doing questions, use the online resources, and continue that process as much as you can, an hour or so, or an hour and a half a day, so that you prepare yourself for the test. So this is also the last section of the course that we're going to be kind of doing heavy, deep, and real with regards to technical information. And it's really important, as I said, to keep in mind that you're responsible for only what's in the book. You're getting a little bit more here to give you a little bit more background and appreciation for the subject area. So the first thing we want to cover with regards to propagation, that is how radio waves move through the atmosphere, is to understand why they move through the atmosphere. And the number one reason, really the only reason, is that solar energy can ionize molecules in the upper atmosphere. And ionization occurs when there's sufficient energy being absorbed by a neutrally charged gas atom, nitrogen or oxygen for example, to cause an electron or more to escape from its influence. So because it's lacking an electron, it's no longer a neutral atom or neutral molecule, we use the term it's being ionized. And that's the important property of what makes propagation actually work with regards to hop or skip through reflecting in the atmosphere. So as I was saying, there's hop and skip, and what we've created is the ionization creates these little kind of, like, for lack of a better term, I like to think of it as RF mirrors. Now we're talking on one level at the atomic or molecular level that these are ionized and they act as little mirrors. And they're all pointing technically, because they're in random motion, in different ways. However, at different places in the atmosphere, they tend, because of their energy level, how much energy they've absorbed, to be in specific locations. And they tend to kind of line up as a whole into a specific direction. And that direction could be pointing straight down, which means signals can bounce off of it straight up and down, or an angle, or even a signal can bounce across that kind of ionized area and move horizontally. And the key here is that the high frequency radio waves, the HF waves particularly, the ones we call shortwave, hit the free electrons in the ionosphere, causing them to vibrate, and this causes them to re-radiate the energy back down at the same frequency, effectively bouncing the radio waves back towards the Earth, as we've been talking about. So just what to keep in mind is that this very energetic area of the atmosphere is able to reflect radio frequencies. And over a 24-hour period, we see the ionosphere is able to break into different parts. And the area we're specifically talking about in the atmosphere is about 30 to 260 miles high, where the solar radiation has energized, as I said before, ionized molecules sufficiently to discharge these electrons. Now, before I get into the different layers, let me just say this. The rate of energizing of these molecules, of these atoms, is, let's say, X. And if that's sufficient, then we can have a lot of ionization going on. However, at the same time that electrons are leaving the atoms or molecules, the atoms and molecules want to become neutral. So they're trying to find electrons to grab onto to become neutral again. So there is always a rate at which these atoms or molecules are trapping an electron and becoming neutral again and no longer ionized. However, if there's enough solar energy hitting that area, the rate of ionization is higher than the rate of recombining. And so therefore we get a higher level of ionization than of recombining. And this is the crux of why we have different layers. So during the day, because we have the sun on the day side giving a lot of energy into the ionosphere, we actually see that we have a number of layers that separate based on energy densities or energetic levels. We have an F2, F1, E, and D layer, and they all have slightly different properties because they're slightly different levels of energy. And then during the night, as things cool down, as the sun is no longer directly hitting that part of the atmosphere, the layers, the F1 and F2 layer combine, and the D layer disappears. And this cycle happens across every day, 24 hours a day, 365 days a week. And it's not sudden. Although the line on this graph shows a very straight demarcation between night and day, of course, we don't have a sudden turning off the lights, so to speak, or turning on the lights. There is a area where there's a transition. We call this the gray line, where everything's transitioning during a specific time of the day between night and day. And so it's not this sudden break, it is actually a very gradual changeover from one to the other. So again, the reason behind these layers changing is the rate of ionization on the sun side is higher than the rate of recombining, and vice versa, the rate of recombining is a bit higher than the rate of ionization, so therefore it flips. So again, we're going to go a little deeper here, but the thing that's powering this whole ionization is UV and X-rays. And X-rays can penetrate much deeper down into what we call the 30 kilometer to just under 75 kilometer range in the atmosphere. And that's where we get the D layer. Then we have an E layer and all the way up to the F2 layer, which are different levels of ultraviolet light, different levels of energy of ultraviolet light. Think of it as different colors or frequencies of ultraviolet light. And so this is what's energizing the molecules to become ionized. So the ionosphere, because of its characteristics, impact bands differently, and the impact varies, of course, as we just said, by the time of day. It also reflects the solar weather. So what's happening on the sun, solar flares, coronal mass ejections, etc., all affect the ionosphere because how much energy it's pushing into the atmosphere, and therefore it affects radio propagation during the course of the day, during the course of the year, and during the course of different solar weather events. So typical ionospheric effects are it can absorb the medium frequencies and lower HF frequencies via the D layer. So the D layer absorbs a lot of the lower frequencies. For example, the AM radio band is medium frequency, and that is absorbed by the D layer. It cannot penetrate beyond the D layer. It gets absorbed. It does not bounce off the D layer and come back to Earth. If you've been, at any time in your life you've listened to AM radio in the daytime versus the nighttime, you'll notice that at the nighttime, you can often hear more distant AM radio stations. For example, in Seattle, you can hear San Francisco radio stations on the AM band at night. Why? Because the D layer is gone. Now the AM can hit the E layer or the F layer, and those layers can actually reflect those frequencies back down to Earth. And so therefore the AM stations can be heard for longer distances. You may have heard the term on AM radio of a clear channel frequency, which means that frequency, that radio station is given the power levels and to be able to propagate to a longer distance, and other stations are either told to reduce power or shut down at night or do not have licenses near where that frequency can be. So a station in Seattle with 50,000 watts could be on a clear channel frequency, which means there are no other stations, would say, in 800 miles that have that same frequency specifically because of this ability to hop. But again, the D layer absorbs medium frequencies and it absorbs the lower HF frequencies, which we call usually 160 meters, 80 meters, and 40 meters. Those are the ones that usually are absorbed by the D layer during the day. So those are local frequencies during the day and become longer hop or more distant frequency uses during the night. Oops. So we can also reflect the RF energy at many RF HF frequencies. So for example, we're talking about the part of the 40 meter band and the 20 meter band and the up to the 10 meter band, generally in the HF frequencies. These energies penetrate the D layer. They penetrate and get reflected off the E, or they get reflected off the F1 or F2 layers. So this is where we have long distance communication during the day and oftentimes at night. So although 40 meters, which is 7 megahertz roughly, is often doesn't go much more than local during the day. At night it can go 800 miles or 1200 miles. And during the day, the 20 meter band, which is 14 megahertz, often can drop to 4,000 or more miles from skip. And on some occasions, the 10 meter band, especially during high solar weather conditions, the 10-meter band can actually open up as far as Seattle into Europe or into Asia at 28 megahertz or so. So depending on the time of day, the solar weather, and the frequency, we have different levels of distance communication in the HF bands. We can also have sporadic impacts to the VHF, specifically the 10 meter, 6 meter, and 2 meter bands, but generally no impact to anything that's really VHF and above. So UHF and above, absolutely, the ionosphere doesn't see it all. There may be some absorption, but if you send an UHF wave into the atmosphere, you're going to see it end up in space. So space communication is generally done at high VHF or UHF and above frequencies. So if you're communicating with, let's say, a satellite or the space station, or you're going to bounce a signal off the moon, you're going to do that in the upper VHF or UHF or greater frequency range, because this passes through the atmosphere with just a little bit of absorption, but does not get reflected back down. However, different types of solar weather conditions can energize different parts of the ionosphere to a higher level, which allows the low VHF segments, like the 10 meter, 6 meter, and 2 meter bands, to every so often sporadically be able to bounce across the ionosphere and come back down to Earth. These are, for those who are interested, this is really a major thing. There are literally information nets across the internet that kind of are the equivalent of surf's up. Let's get surf is up. Let's get on the air, because it's not a usual occurrence. But when it happens, you can take what usually is a short range communication at VHF or UHF terrestrially to become much longer. So we've talked about this bouncing and a few other things. Let's go a little bit more deeper and talk about the three types of radio waves coming off the antenna. We have a ground wave, which basically is kind of running at the ground level. It tends to bend with the Earth. It actually has a longer, the space and ground waves have a longer horizon than the visual horizon, though. And then we have a space wave, which is a direct path, generally speaking, between antenna A, the transmitting antenna, and antenna B, the receiving antenna. And then we have a sky wave, and the sky wave is going into the ionosphere, and in case of VHF and above, it's basically going right through the ionosphere into space and never returning or being hit by a satellite, and the satellite then retransmits it down at a different frequency. So what I want to clear up here is that there is no distinct three waves. These are waves coming off the antenna, and that doesn't mean that there's a distinct area for sky wave, a distinct area for space wave, a distinct area for ground wave. As these waveforms come off the antenna, they're coming off at different angles, and so therefore they have these characteristics. But you won't find a demarcation between these. You'll just find certain wave angles come off at this, and certain wave comes off the antenna at that, and they tend to have these groupings that this is a sky wave, this is a space wave, which is direct path, and this is a ground wave. Now at the HF frequencies that we just mentioned, we have a sky wave that has the ability to be bounced off the ionosphere, hit those little mirrors and be reflected down. And of course, this also applies to some special times, as I mentioned before, for parts of the VHF spectrum. So propagation is really radio frequency going from point A to other points. And notice I didn't say from point A to point B, I said to other points, because we're really not always clear what the other points are, because we don't know. Because of the wavefront, a radio transmission leaving the antenna can be hitting antenna B, antenna Z, antenna Q. It could go in different, depending on what the geography is, the distances, etc. But overall, RF travels in a straight line like light does. And the energy level falls off as an inverse square of the distance. That's the signal's range. So the further away you get from a radio transmission line or a radio transmission antenna, the less energy that has as the wavefront spreads out in space, and therefore the energy falls off as an inverse square of the distance, and that's the signal's range. And RF can penetrate some materials based on frequency energy level. Shorter wavelengths are favored, so things like UHF, which has a very short wavelength compared to HF, can often travel through a building and be useful for transmission and receiving. versus something in the HF range, the shorter waves, may not be able to penetrate a building very effectively, and therefore transmitting inside the building will be much less effective than having the antenna outside the building. And there are three things that can happen, and they're kind of all could happen at the same time. And specifically, RF can be absorbed by the ionosphere, it can be reflected by the ionosphere, or it can be refracted or bent by the ionosphere. However, anytime a radio wave is going through the ionosphere, some of it may lose, some of the energy may be absorbed, and you can have energy being reflected and refracted depending on how it hits, what each, as I said, the little mirrors are pointed in different directions oftentimes, and so therefore it's all three of these things can happen to the radio wave at the same time. However, the dominant one at different times of day and at different frequencies could be absorbed, like in the D layer for medium waves, medium frequencies, or reflected in the HF band in the ionosphere rather than being absorbed or refracted. So again, all three can happen, but there's usually a dominant one that happens for a specific band at a specific time of day and solar weather condition. And then RF hitting a reflected surface, this is the angle of reflection equals the angle of incidence. And you can see that on the right is if we see the solid red line is the radio wave coming up and hitting this mirror, so to speak, or a light hitting this mirror. It's the same thing in this case. And the angle it hits the mirror is the same angle it's reflected of. So the angle A, as you see here, is equal to the angle B. So the angle of incidence is equal to the angle of reflectance. And RF, it's really important, is non-ionizing form of radiation. It does have the potential to heat. Yes, like microwaves in the oven can heat, but they're not ionizing like radiation is an ionizing form of energy. RF is non-ionizing, that is, when it hits a human body, for example, it is not displacing electrons. Whereas X-rays, for example, and gamma rays are ionizing radiation. That is, when they hit your body, they will displace electrons or disrupt the nucleus of an atom. But RF does not do that. What RF can do, if it's at a high enough frequency and a high enough energy level, it can produce heating, as I said, in a microwave oven. Now, as I said, RF can be reflected, refracted, or diffracted. So radio waves are reflected by any conductive surface like ground, water, and buildings. Yes, even though ground is really not a great conductor, it does have some level of conductivity. Water, although neutral, does have some absorption or reflectivity of RF. And if you live near salt water, it actually is a great conductor. So therefore, it actually does a great job of helping reflect a wave against it. And buildings, a source of metal, can also be used as a reflective surface. Refraction, as I said before, or bending, occurs when waves encounter a medium having a different speed of light. And as we travel through the atmosphere, because the medium is different densities, we can see some slight change in the speed of light, or in this case, the speed of the radio wave, and therefore we can create a radio horizon, which means the radio wave can travel slightly further than the visual horizon. And then we have diffraction, which occurs when VHF and UHF waves encounter a sharp edge, what we call knife edge propagation, or hit a corner of a building, for example, to create an interference pattern. As you can see on the right, the interference pattern is such that we're going to have live zones where we can hear the signal and dead zones we won't hear anything. And that's the result of knife edge propagation. Now, knife edge propagation can be useful because sometimes you can use it to help you bounce the signal off in such a way to hit something or get to another antenna that you normally could not get to with just line of sight. And we talked a little bit about this, I think, before, but multipath signals, which are signals that are coming from the antenna, the transmitting antenna, to the receiver, but because of reflections and direct path, you can have all these signals hitting the receiving antenna at various times, and that's multipath. Well, look at these multipaths on the right. Notice that they're all taking a different path and they're all covering a different distance. So the same RF energy signal can be interfere with itself when the receiving antenna picks up the signal from different paths. And this means that each path takes a different amount of time, therefore it enters the antenna at a different phase relative to the original signal. Because it took longer for one path to get there to the antenna than the other, we're coming in slightly out of phase each time. The one that took longer to the longer path is delayed with respect to the one that took the shorter path. They're hitting the antenna, and when they hit the antenna, they're interfering with each other. And as we learned earlier, different phases can either sum to be greater than, or less, or subtract, become less than, and therefore you can either have a signal boosted, that is, it's in phase and the volume goes up, so to speak, or the energy level goes up, or they're out of phase sufficiently enough that they're subtracting, and therefore we can have a reduced volume or reduced intensity signal, even to the point where the signal disappears for some period of time, because the waveforms hitting the antenna are interfering with each other and canceling each other out. So again, different multipaths will have impacts to the energy hitting the antenna. They'll either add to the energy or they'll subtract the energy and anywhere in between. And that can create the fading that you hear when the signal is being received by the antenna. It's fading in and fading out, and that is from multipath. And oftentimes, the way that you can do if you have a fixed receiving station is to change the position of the antenna to a point where you've minimized the multipath interference. So another aspect is when you're operating a station mobile. So you can see on the right, there's the antenna at the back of my car. It's a dual band VHF UHF mobile antenna. When I'm around the city driving normally, the antenna is mounted, as you can see, at the back of my car. Not the best place with that big body of metal sitting there. However, if I'm doing a long distance trip, I have another mount at the top of the car, which then gives me more range because at the top of the car the metal is now acting in a different way. It doesn't interfere in the same way. And so therefore I get better range when I'm in a situation where I don't have to worry about the height of the car and the antenna. But as we're driving, if we're listening to other stations when we're driving, then there's a possibility that we may hear mobile stations that go in and out because of multipath dead spots or areas that we call areas of high attenuation. If amplification is to increase the strength of a signal, attenuation is the opposite. It decreases the strength of a signal. And this will sound to you when you're listening to a station that's moving and transmitting as a rapid flutter, or what we call picket fencing. And you'll hear it sort of this rapid flutter, and it almost sounds like it just sort of sounds like you're hearing sound through a picket fence, or if you ever shouted through a fan, you might have the same effect. And so one of the other results is if you're doing data-based data transmissions, if you're transmitting data like in modes like FT8 or JT65, and this one station is moving, it can cause the data signals to have a higher error rates. If it has a higher error rate, there's going to be less information passed, or there's going to have to be, because of the inherent error correction of some of the digital modes, it will slow down transmission as the computer keeps asking for a repeating of the missed parts of the signal. So again, this happens when you're mobile, and it happens when you're going through different multipath dead zones. And the ultimate mobile, of course, is amateur radio operators operating from the International Space Station. So there is two different stations on the International Space Station. One is a fixed station, that is, that's not used by the astronauts at all. What it is, its job is to act as a amateur radio satellite. So we have a network of amateur radio satellites. One of the satellites in the network is the International Space Station. It has on board a receiving antenna and receiving radio, and a transmitting antenna and transmitting radio. And what it does, like any other satellite, it picks up the receiving frequency and then retransmits it on the transmitting frequency. One's called an uplink. So if I'm transmitting to the ISS, let's say at VHF, then it's going to retransmit the signal as a downlink on the UHF band, and that's where I'll be listening to it. So here we have the astronaut using the astronaut station, which they often do. And so when they have some free time, they'll make contacts from the space station. And if you have entered the orbital data into some of the applications, you'll be able to track the ISS. You can use as little as your 5-watt handy-talkie if you're quick enough to change frequencies for Doppler shift, which we won't get into, but you'll be able to at least hear or even make contact with the ISS. By the way, almost all of the school interviews that happen with the astronauts are happening on the amateur radio band, being facilitated by amateur radio operators. So we've talked about basically how the ionosphere gets energized and can reflect radio waves. There is also another type of propagation that can occur, which is tropospheric propagation, which happens to the VHF and higher frequencies, and it's called ducting. And the troposphere is about 30 miles high, and as I said, it can reflect or scattered. It can be reflect energy, VHF, UHF energy, or scattered, and it can be scattered by clouds, rain, and density variations in the atmosphere. And temperature inversions and weather fronts can form ducts or traps that conduct these waves for hundreds of miles. And so you see in the illustration, you can have cool, dry air at the top and cool, dry ocean air at the bottom, and then you have moist air trapped in between, and that can create a tropospheric duct, which allows VHF and higher transmitters and receivers or transmission to be heard for longer distances as the VHF or higher frequencies are bounced across this duct to another location, further than they would have done if it wasn't there. And so, again, this favors the VHF and higher frequencies. UHF and higher more likely is the generally it's UHF and higher, but it can affect VHF as well. And this is done basically by changes in clouds, rain, and density variations in the atmosphere. Don't worry, you don't have to know this, but this just gives you some ideas of how things function. Here's on the left top, normal conditions. You see the purple and the green lines, and it's basically coming from the transmitter. You can see the far right, the receiving antenna over on that downward part of the curve or the earth. And you can see that, this is line of sight. We see the VHF and higher frequencies basically traveling up and continuing to go up. And we can see the bottom green line, that first green line, or the sky wave, not the sky wave, but the space wave, is just hitting above that transmission, that receiving antenna. On the far right, you can see that green line is just above that receiving antenna, which means that receiving antenna cannot hear the signal because it's not touching that antenna. And then on the right top side, we see the super refraction, where the signals are bent down. And here we have the warm, dry air and the cold, cool, moist air. And now we can see that different parts of this radiating signal from the transmitting antenna are ducted or bent down, and one of the waveforms that's bent down touches the receiving antenna on the right. So therefore, that transmission is being received, and it's being received at a place where normally it could not be received, as we look at normal being on the left side there in the top. And then we have stronger ducting here on the right, on the lower left. And again, we're seeing in this case the ducting is strong, and we see the ground reflection being picked up by the receiving antenna. And then we have elevated ducting, as you see on the right. Again, you're not responsible for this kind of complexity, but just to give you some idea of how these things function with respect to the waveforms coming off the antenna. And here's an example of a number of amateurs. What this picture shows, not showing, is that this goes on for about 7 or 8 cars, all similar setups. And they're working at the 10 gigahertz range, which has a wavelength of 1.17 inches. And they're using the inversion layer to basically extend the range of their transmission. So the images, as you say, shows Ham's attempting to use the inversion layer to extend the range via their ducting of a 10 gigahertz signal near Washington, New Hampshire. And to keep in mind that with these frequencies, at the UHF and higher frequencies, rain and fog can impact signal path and strength of UHF at these frequencies. And as we showed before, there's something called tropospheric ducting that can favor these kind of these bands so that they can be ducted and travel longer distances. And of course, vegetation can absorb VHF and UHF frequencies, which means if you're trying to transmit through a forest, you're not going to have the same signal strength as if you were transmitting in open air. So the higher the frequency, the more and more it acts like light, until eventually you get to a point where when you're making contact, even at 10 gigahertz, you're often making contact, if it wasn't for this inversion layer, you're making contact with another amateur radio because you've scheduled the contact, because you have to aim these antennas because the wavelength is so small. You literally have to aim these antennas directly at each other and coordinate that till you're lined up because the wavelength is so small. So things can get really, really complex when we're talking about bouncing signals around the ionosphere. Because the densities vary from less to more dense across the polar, temperate, and equatorial regions of the Earth, we're going to see different ducting characteristics happen because the energy levels in the ionosphere are changing or different at these different regions because of the way the sun hits these areas of the Earth, and also relative to the seasons that we go through. So around the equator, we have what's called transequatorial ducting. You can imagine that's a very higher energy area around the Earth because this is where the sun is almost always directly overhead. And this extends about 5,000 miles around the equatorial, can't talk, around the equator of the Earth, I'm sorry. And so this is a special ducting that lets a signal bounce back and forth across this 5,000 mile window much easier than it would have in the polar or temperate zones. We also have sporadic E, which I mentioned earlier, which is a kind of a very transient, localized phenomenon that happens in the E layer, where because of solar weather, a specific area of the E region has become more energized, and it's become so energized that the VHF frequencies around the 10 meter, 6 meter, and 2 meter area can now be reflected back down to Earth, which extends the range of those communications across the globe. Usually from up to 600 to 1,200 kilometers is not unusual. 10 meters even more, but I was just talking about 2 meters. But 10 meters, it can be much longer. And then we have meteor scatter. This is a very specialized area of amateur radio where people will bounce signal off the ionization trails of meteors. There's always meteors or dust, particles hitting the Earth's atmosphere, burning up, creating an ionization layer, ionization trail, excuse me, and you can literally bounce signals off of them, and it's where you also would hear some types of fading that occur because it's a very irregular type of ionospheric or ion trail, and it's best at the 6 meter or 50 megahertz range, and of course you have more opportunities when there's meteor showers, but there's always some level of dust and such hitting the atmosphere causing an ionization to occur, and some people in the hobby really enjoy chasing after that. Kind of the same line of ionization is the aurora, whether it's the southern or northern lights, creates distortion, and you can, if it's not super energized, you can oftentimes bounce the signal off the aurora and create a reflected wave. It's not unusual for people in, let's say, Alaska to aim their antennas towards the aurora to be able to reflect back to get the continental United States. So they're taking advantage of that aurora bounce to be able to contact other parts of the world, specifically continental United States. But because it's undulating, it's moving, and it's changing all the time, there can be some distortion that comes when you're trying to decode the signal into, let's say, audio or something. You'll hear some distortion. And then we have two special situations. One is what's called the maximum usable frequency, and the other is the lowest usable frequency. So the maximum usable frequency is at what point does a radio frequency no longer get reflected by the ionosphere? When you get a frequency that is higher than what is reflected by the ionosphere, it will pass through the ionosphere and go into space. So what we try to do is find out what is the maximum usable frequency. That is, what is the frequency by which you can always or most of the time reflect off the ionosphere. And the lowest usable frequency is the frequency by which an energy will pass and be reflected by the ionosphere instead of being absorbed by it. So remember I talked about the D region can absorb frequencies in the medium frequency and low HF ranges, and therefore if during the daytime the lowest usable frequency is going to be relatively higher than at night when the D layer is gone, you'll have a lower usable frequency than you had during the day. Oftentimes we don't worry too much about the LUF, but at the MUF varies day to day based on solar conditions and the ionospheric conditions that result from the solar conditions, and so that can vary. It can vary through the course of the day. So generally speaking, we can look at space weather reports and find out what the maximum usable frequency is, which tells us that if we want to do long distance communications, for example, in the 10 meter band, we can see the MUF, which the 10 meter band is about 28 megahertz. we might find the MUF is good for 21 megahertz, which means we probably are not going to get much long distance communication with the 10-meter band because the 10-meter band is higher than the MUF. And one of the other things about waves that are being reflected by the ionosphere is they come back elliptically polarized. Elliptically polarized. And we'll talk a little bit more about polarization in a little bit, but just keep that in mind as these waves become, and I got to fix that. Just notice it's WASES. Sorry, I'll have to fix that to waves. Reflected waves become elliptically polarized, and we'll get into what that means a little bit more, but just keep in mind that for HF, this is why polarization of an antenna has very little effect in the HF bands, but it has a major effect in the VHF and above bands, and we'll get into why a little bit. Of course, we took a very simple approach to the ionosphere, and you don't have to take much more than the approach we just took. However, I use this picture to give you an appreciation for how complex the ionosphere is and all the things that influence it, whether it's the sun, it's winds in the upper atmosphere, it's the magnetosphere. There's so much that affects the ionosphere. It's so much more complex and dynamic than I can even explain here. And if you want, there's a lot of information out there about this. It's an area we're still learning about. There's ham radio operators who are involved in doing ionospheric research as part of a community that involves the National Oceanic Atmospheric Administration as well. We do monitor, we have space weather and reports that we look at as well for those kind of interactions. Not so much as VHF and UHF and above situations, but if you're like me and operate lots of HF, for long distance communications, I'm always attuned to what's happening in the space weather and the ionosphere to see what I should be doing with my radio for that given period of time. But again, this picture is not to go, oh my, I have to learn this for the test. No, I just want you to have an appreciation for how complex our world really is. Now, if you really want to get into this, there's lots of information about it, and we have on the left side a screenshot from the National Oceanic Atmospheric Administration, NOAA. You can see the website down there for the space weather conditions. It's also a great place if you want to find out if the aurora is going to be able to be visible in Washington State. We also are looking at the different solar wind situations that are coming across towards the Earth. And so the sun, as I've been saying, drives it all, and we're driving it all through the sun's general energy, the solar wind, and also sunspots, coronal mass ejections, and flares. And of course, as you may remember, solar activity varies over time, like an 11-year sunspot cycle. And currently, we are, if you look at the graph on the right, we are in the upturn of solar cycle 25 of the 11 years, this 11-year cycle. And just was announced recently that the sun has flipped its north and south pole, which means we've hit solar maximum. And this is where we're going to get a lot more energy coming out of the sun for the next year or two, which is oftentimes great for us in the HF propagation range. What you see on the red line is what the original prediction is, and what you see in the black and blue line, or black and purple line, is what's actually occurring, and it's much more energetic than was originally predicted. Below that, you can see the changes in the solar cycle from before the 1800s to current time, and how much it varies over a course of time. And you can see the there is a pattern there, and you can see there are patterns that are longer than 11-year cycles that we're not going to get into. But just so you know that there is space weather reports, and you can look at them. And if you're interested in long-distance propagation, this is a great place to start if you want to go get more and more information about that. Of course, there is HF frequencies, although limited, available for technicians. And of course, besides the space weather at NOAA, we have a number of different broadcasters. And here we have on YouTube the Space Weather Woman, and she is very popular. She is a PhD in this subject, and she gives out reports on what's happening with the sun, and you can always use that URL to listen to her broadcast on YouTube, and she gets into a lot of detail for amateur radio, for pilots, and for people who are taking photographs of auroras. Those are some of the people she addresses. So this is how I have a 1 hour lecture on the ionosphere and propagation that I give to radio amateur clubs. And one of the things I like to leave them with is the Earth is a rotisserie chicken. And and the less and this is the one of the title slide from that lecture. And the reason I want you to think about that is that think of whether you go to Costco or wherever, and you see a chicken rotating around a hot source. It's a rotisserie chicken, and that is hot source is the sun. And you can see as the chicken is rotating, there is a hot side and a cooler side. So the daytime side is facing the hot source, the heat source, and the nighttime side is on the other side, which is away from the heat source. And as it turns, you can see the temperature gradient of that chicken is changing as it turns, which means the ionosphere, in the case of the Earth, is changing as the Earth turns. And then of course, the ionosphere is rotating around the heat source in 360 degrees, so to speak. And so, so it's changing over time, not only in a 24-hour day, but in the yearly cycle. And so that's the way to look at the ionosphere. It to me is it's a rotisserie chicken. The Earth is a rotisserie chicken, and the heat gradient across the chicken is the level of energy of the ionosphere. And you can see that when it's highly energized, where it's facing the heat source, there's more possibility for reflection. And on the darker side, or away from the heat source, there is less energy, so less reflection that goes on. So just kind of fun to keep that in mind. That that's the analogy I tend to use, or maybe the metaphor I guess I'm using. So enough for that. Let's talk about antennas. We're getting into the heart of the matter now. And this is basically what a speaker is to a stereo, an antenna is to a transmitter. So you can have, not so great stereos, but if you've got really, really good speakers, the stereo sounds really, really good. And of course, if you have really, really good stereo and really good antennas, it's even better. But a stereo that doesn't have a really great power output is improved by a good speaker. So antennas, as we said, can release and or receive RF radiation. We've kind of been saying that across the last couple of sessions. And these are all examples of VHF antennas that are capable of receiving and transmitting. Of course, the way these antennas work, or generally these antennas work, is they can receive and then they transmit, then they receive. They can't do both at the same time. However, there is our setup that allows them to do both at the same time, and that's how repeaters work. And I have a special device that sits below the antenna that allows the one antenna to be used for simultaneous receiving and transmitting. The way they do that is that they receive on one frequency and they transmit at the other frequency. So they don't do both at the same time. But these antennas in general are receiving and transmitting at the same frequency. They can only do one or the other at a given moment in time. So we have, like I said, different antennas, different configurations, and we'll get into some of these configurations. But their only task is to release RF energy or to receive RF energy. So let's look at the anatomy of a dipole antenna, because that's the most basic antenna that we have. Sometimes every antenna is a dipole in different configurations. So they may not look exactly the same, but when you dissect them, they all tend to look like dipoles. So a dipole has a radiating element. It has a left side radiating element or left side leg. It has a right side radiating element or right side leg. These are designed to be about a half wavelength, although they could be quarter wavelengths, they could be eighth wavelengths, they could be 2 wavelengths, they could be 5/8 wavelengths. Different wavelengths have different properties, but they're usually some sort of equal multiple of a wavelength. The place where the elements come to meet the feed line is called the feed point. And the feed line or the transmission line goes to the feed point. So we are moving the energy from the radio through the feed line to the feed point, and at the feed point it's being driven to the elements, and when the RF energy hits the elements, it's going to then radiate into space. And this is a horizontal dipole. We can also have vertical dipoles. It's the same situation, except it's turned vertically, and we have a feed line coming off at perpendicular to the vertical, or 90 degrees to the vertical. And we have a center positive side and a negative side, so to speak, although in alternating current, in RF, it doesn't exactly work that way, but we do that for convention. It's easier to talk about about it this way. So same thing, we have a feed point, a feed line, and elements. Now, this is straight up and down, it's a vertical, but we can also have a vertical where one element is straight up and the other elements are the ground elements, so to speak, the negative elements, are horizontal. And that we call a ground plane. And so again, we have a feed point and we have the elements and we have a feed line, and that is also a vertical. And if you think about it, if you take one of the elements on the far right vertical away, just for illustration purposes, you'll notice that if I start moving the left side ground element more and more vertically downwards, it will eventually become the vertical in the center because they're equivalent. What happens though is some things are changing in the way this radiates and in characteristic impedance. When I move that lower element, that negative element, so to speak, or that ground element, down from horizontal to vertical, there are things that change with the antenna. Now, this far right one you can look at as I just put an antenna on top of my car, and the bottom element could be the car's metal itself. Or if I have a handy-talkie, remember we see almost every antenna has to have two parts. There's a sort of a left side or right side, or a positive side or a negative side, for lack of better terms. When you have a handy-talkie, there's only one piece of the antenna coming out of the walkie-talkie, or the handy-talkie, and that's the vertical. So where is the other side of that antenna? It's you. When you touch that handy-talkie, you become the other part of that antenna. It's not that handy-talkie antennas are not very efficient. They get the job done for what they're designed to do, and you become the return element in that signal path. So we talked about resonance, and we said, remember, that resonance only occurs at one frequency, and all antennas have a point at which they resonate, where there's only one and only one frequency where the inductive reactance, X of L, is canceled out by the capacitive reactance, X of C, leaving only the internal resistance of the conductors. So remember that formula we have on the right side here, which is impedance, Z impedance equals X of L plus X of C plus R. But at resonance, we have X of L is being added to a minus X of C, which equals 0, which leaves us only the ohmic resistance, the ohms. And that's where we know we have resonance. When that happens, we have resonance, which means that essentially the wire we have, the antenna going to the coil and the capacitor on the right, when we're at resonance, what happens is that as if those two components disappear, and all we have is a straight wire from the top of the antenna to the radio, and only the internal resistance of the wire is left. That's resonance. That's what happens at resonance, is the L's and C cancel out and it becomes like if they don't exist, that there's just one shorted wire from one end of that terminal to the next, and therefore we have maximized the current flow through the antenna. And that happens only at one specific frequency, unless we have a variable capacitor or a variable inductor. But in this case, we don't. So there's only one and one frequency where the antenna is resonant. So what influences the resonant frequency? The length of the conductive elements, because remember I told you, is that, for lack of a better analogy, antennas are like tuning forks. Their physical characteristics determine what they vibrate at. The physical length of an antenna, the diameter of its elements, the material it's made out of, if it's insulated or not, and the nearby environment, if there's any metal nearby, all influence what the resonant point of that antenna is going to be. Now, we have an antenna that's really maximized to work at one frequency, we call the center frequency. And as we move away from the center frequency, the amount of power we can receive or transmit is lost to heat. Basically, it's not as efficient at radiating, and that inefficiency means that's, even though it may not be, you wouldn't not necessarily always can touch the antenna and feel it's getting hot, it is causing the antenna to heat up when it's off frequency, because it's not radiating all the energy. It's going to go somewhere. It's going to go out as heat, even though that heat may be so small it's almost imperceptible at times. And if you have enough power, it might be perceptible, so be careful. So we have this center frequency, and then we have we have two other frequencies, which I won't get into details of what the 3 dB point means, but it means that we've considered, based on the design of our antenna and the design of our receiving unit and transmitting unit, that we have acceptable losses on either side of the center frequency called W1 and W2. As long as we are in those acceptable losses, we consider that antenna to have a bandwidth of, let's say, X. Between W1 and W2 is X. If we go beyond those points, then the amount of power loss through the antenna is higher and we won't be radiating as much energy. So although an antenna only has one center frequency, we know that that antenna will work on a wider range of frequencies, not as efficiently as the center frequency, but efficiently enough that we can use it without significant losses. So again, although there will be power losses when moving from the center frequency, the bandwidth is an area where there is an acceptable amount of losses compared to what we're going to, our gains in transmitting. And so that 3 dB happens to tell me how much power loss is acceptable that defines the bandwidth of this antenna. But again, if the frequency is 14.2 megahertz, then we would love to see the bandwidth to be somewhere between 14 and 14.35 megahertz, because that happens to be the voice band of the 20-meter band. But you can be tighter. You can be much tighter. It all depends on the design of the antenna. And there are benefits to being tighter in this bandwidth, and there are some benefits to being wider in this bandwidth. But again, it also is a trade-off between losses and energy released that you have to make some trade-offs in. But all we have to do for this course is understand that every antenna has a center frequency that it's optimized for, and there's an acceptable bandwidth on either side of that frequency, that center frequency, that we find usable for most of our transceivers. So let's say we want to find the resonance given a length of elements. Remember I said that the elements, as we've talked about before, are based on the frequency. So what length of wire do we need to create a half-wave dipole at 224 megahertz? As you can see, we just use the circle here, and we can find that we get a wavelength of 1.34 meters. And if we're going to design a half-wave dipole, we need to know that it has to be half the wavelength, and we know the wavelength is 1.34 meters, so we divide that by 2 and get 0.67 meters or 26.12 inches. And so we would design a half-wave antenna that would then have a 26.12 inches for the element. Now there's another equation. This is the one we traditionally use for actually calculating the elements of an antenna, for a dipole antenna specifically, and this will always give us the results in feet. So instead of using 300, we use the constant 468. There are a number of different constants that are in place of 468. There's even 492 that have been used experimentally to find out how close can you get to the right length for a dipole. And it's been kind of decided by the community of amateur radio operators that 468 is going to get you close enough as a starting point to build your antenna. So if you want to find the approximation of a half-wave dipole in feet, remember the first equation was 300 gives me the full length, the full wavelength. This equation gives me for a half-wave dipole, and we can see that it is 2.1 feet or 25.1 inches will be the half-wave dipole in feet. If I need a quarter-wave dipole, I just divide that by 2. If I need an eighth-wave dipole, I divide that by 4. And so this will get me close enough for this dipole, for a half-wave dipole. There is a difference between these two formulas so that you don't get exactly the same number. But in practice, when we're designing an antenna, we use that 468 number instead to give us the length in feet. And it's general practice if you're building your own antenna that we always build the antenna longer than we calculated for. So if I were building this antenna for 25.1 inches, I'd probably cut the antenna initially for like 28 or 29 inches. And then as I use a special device called an antenna analyzer or an SWR meter, as I go to the frequency I want to design for, I may start cutting some wire off this antenna until the antenna is at the right resonant frequency that I want. And so the tendency for this formula is to always cut longer and then trim it back, because it's easier to cut the antenna smaller than it is to start welding in wire to make it longer. So we have horizontal and vertical dipoles, and does it make a difference for VHF and above? Well, the RF wave can be moving horizontally or vertically through space due to the orientation of the transmitting antenna. A receiving antenna oriented like the transmitting one maximizes the surface wave front that it can interact with. And this is called antenna polarization. So if you look at our vertical antenna here, and we have a horizontal wave coming across this vertical antenna. So if you think about your left arm is the vertical antenna, and your right arm, your palm is horizontal on the right arm, and your left arm is vertical. You can see that very little wave is interacting with the surface of the antenna when it's horizontal. Versus vertical, if I have my right arm up, and the wavefront is on the other arm is in the same orientation and it's coming through, you can see it's interacting with the entire antenna. So there's more surface area, more energy transfer. So when we're dealing with space waves and ground waves, it's important in VHF and above to have the same vertical or horizontal orientation. So the transmitting antenna should be oriented the same as a vertical and vice versa to maximize the amount of energy transferred. And so by convention, we have decided that when we're doing frequency modulation, FM transmission in the VHF and above ranges, we use vertical orientation, vertical polarization. That is, both antennas are set up to be verticals. And in the VHF and above ranges, if we're using what's called SSB, which you'll learn about later, single sideband or data transmission, we often will use horizontal orientation. So the way for the antenna will be turned horizontally for the receiving and the transmitting antenna. So this doesn't make any difference when it comes to HF from the point of view of polarization, because once you bounce through the ionosphere and come back down, you're now elliptically polarized. You're kind of traveling in a circular polarization. And therefore, it doesn't matter if you're horizontal or vertical. It's equally not as efficient. There's nothing you can do about that. But for FM, for VHF and above transmissions, because we're using ground and space wave, the antenna orientations between the transmission and the receiver need to be the same to maximize the transfer of energy between the two. So again, FM, we've agreed that it's going to be vertical orientation, and for SSB, single sideband or data, we're going to use horizontal orientation. Now the other thing is, we have the transmitter, it's trying to deliver, let's say 100 watts or 20 watts or 5 watts to the antenna, and we have to get that energy to the antenna. Well, it's possible that even though the energy is going out of the transmitter, it may not fully get to radiate. Why? Because we have to transfer that energy efficiently to the antenna. And the antenna is designed for a specific impedance. And that impedance will vary with the characteristics of the antenna, the design of the antenna, its height above the ground, and other factors. So therefore, we have to find a way to maximize the transfer of energy, and that we do this by making sure the impedances match across the whole system. So to get maximum power transfer, you have to have the impedances match from the transmitter to the antenna. And the transceivers are built to provide a maximum output at 50 ohms. Therefore, if you want maximum transfer to the antenna, you have to have a 50 ohm impedance matched to whatever the antenna impedance is. And we have devices for doing that. So the one on the top right is called an un or a balun, and we won't go into the differences right now, other than to say that it's an impedance transformer. So remember, we talked about transformers earlier. Transformers can transform voltage either higher or lower, but they can also transform impedances higher or lower or vice versa. So here we're looking at a transformer that transforms the 50 ohms from the transmitter to 450 ohms this antenna design needs. This is a 4-to-1 transformer because it's boosting it up from 50 to 4. Excuse me, I should have said a 9-to-1. Sorry, it's a 9-to-1 transformer because you can divide 450 divided by 50 is 9. So it's a 9-to-1 transformer. And this one is specifically called an un. We'll talk about that later, what an un is versus a balun and what that means. But this is an impedance transformation that takes the transmission impedance, the transceiver's impedance at 50 ohms, and converts it to 450 ohms with this design antenna needs. So for example, this would be an N-fed half-wave dipole antenna, which traditionally, an N-fed random wire antenna, an N-fed random wire antenna, which traditionally has an impedance of 450 ohms. So we use a transformer to make that adjustment. Below that, we see a circuit, which is an inductor and a variable capacitor. And we can tap the inductor, at different places because of different band needs that we want. And what we do is we vary the capacitance, or we vary the position of the coil through these taps on that switch. And what we're doing is doing an impedance transformation. So you can do an impedance transformation like you do above with some wire across a toroid, or we can use the variable inductors and variable capacitance to adjust those to do the impedance transformation to match the transmission line to the antenna. Now in VHF handy talkies and some of the VHF, we don't worry about this too much. We have ways of dealing with it that are a little bit different, but it's still the same idea holds true. If you want to get maximum transfer of energy, you need to make sure that the transmitter's impedance matches the antenna's impedance, and you have to do that through either an impedance transformer like we have above, or through a matching network like the L network that's below. And again, if you're using a handy talkie primarily, it's not going to have perfect power transfer because it's a very inefficient antenna. But there are ways to deal with that, which is you can use an external antenna, which is designed better than a handy talkie antenna. But for the versatility of a handy talkie, you're going to just accept the losses and know that you probably have enough energy to hit the repeater or line of sight communications that you need. But if you want to have the best range possible, then you would do things to improve the energy transfer to the antenna and be able to make sure the impedances match. And so you can do that. It's just up to what your choices are. In HF, it's almost automatic you have to do this. In VHF power levels that we use, we often don't have to worry as much about it in low power levels. So this is one of the things that confuse people a lot because we talk a lot of in decibels in amateur radio. Actually, in any type of amplification or measuring antennas or anything like that, we use power levels. And the power level values that we use are in the unit decibels. And it's computed using logarithms so that the very large and small ratios results in numbers that are easy to work with. And so there are formulas you can memorize. You don't have to. The chart on the left is really all you need to learn. And that is that as decibels go up, the power is going to go up significantly. So at 0 decibels, we're basically, if we have 100 watts, the power from the original is going to be 100 watts. So if we have a 100 watts transmitter, at 0 decibels, it's going to be 100 watts output. If my amplifier is able to double the power, so that we're going to go from 100 watts to 200 watts, the decibels goes up to 3. So 3 decibels means we've doubled the power. 6 decibels means we've quadrupled the power. 9 decibel increase, we have now bring the power up by a factor of 8 times. So if you know these ratios, 0, 3, 6, 9 is 0 is 1, 3 is 2 times the power, 6 is 4 times the power, 9 is 8 times the power, you can interpolate other values to get an approximation, and that'd be good enough for amateur radio work. On the other side, we're going to lose power. We have the minus 3 point, the minus 6 dB point, and the minus 9 dB point, and you can see the reverse is true. What minus 3 dB point is half power. Minus 6 dB point is quarter power. Minus 9 dB point is an eighth of the power. So if I were to have a transmission cable that has a 3 dB loss, it means that if I have a 100 watt transmission coming from my transceiver and I have a 3 dB loss, it means what comes to the antenna is only 50 watts. It's only 50 watts. So this is, we need to know this because there are certain things we want to know. We want to be able to compare how good one antenna is to another. We want to compare how one antenna amplifier is good compared to another. So we use the dBs. And there are certain other abbreviations that you'll find. dBm, which is the dBs related to 1 milliwatt. Oftentimes in dealing with antennas, we're dealing with dBms. When we talk about energy levels hitting an antenna, dBi is the gain of an isotropic antenna. So somebody might be buying an antenna and it says, well, this antenna is $300 and it's got a gain of 4 dBi. That means it's got a gain that's 4 decibels bigger than the isotropic antenna. Well, an isotropic means it's an antenna designed in an ideal condition in free space. It's floating in a imaginary world where nothing is near it and nothing can interfere. It's the ideal condition antenna. And so that's that's just a way of comparing one antenna to another. And DBD is the maximum gain of a half-wave dipole in free space. Free space is the equivalent of what we use the word isotropic for. So that is a DBD, and it's the maximum gain of the half-wave dipole in this isotropic condition, in this free space condition. So if someone says, oh, my antenna that I just built has 2 dB of gain, it means it has 2 decibels of gain over the half-wave antenna in free space. Again, it's DBD and dBi are the ones that you primarily will see in amateur radio and the technician level, and we use it to compare one antenna to another and as relative to its performance. So you might see a gain, let's say for example, some antennas like a vertical antenna that's ground mounted may have a negative dB compared to a half space dipole in free space. So that's also possible that you will have an antenna that's not as good as the DBD reference antenna. So again, if you memorize the chart on the left, you'll very quickly be able to answer any question in the technician and the general test on dBs. So I talked about this a little bit ago, and this was, I think, in one of the early classes on spurious emissions. And I wanted to use this as an example. You don't have to know this for the test, but I want you to understand this when you're buying your equipment. So there is part 97.307, part E for VHF and above, is part of the Title 47, part 97 rules that govern amateur radio. And it says, for a transmitter having a mean power of 25 watts or less, like a handy-talkie, the mean power of any spurious emission supplied to the antenna transmission line must not exceed 25 microwatts and must be at least 40 dB below, that's negative 40 dB below, the mean power of the fundamental emission. Which means that when you have amplification going on or mixing going on to create the radio signal, you create products along the same time. So you can rate harmonic products. And a good radio filters those harmonic products out, so all you're left is the center frequency. That big spike on the left in yellow is the center frequency. That is the frequency of the transmission. And you can see there's a bunch of little spikes of second, third, fourth, and fifth harmonics, and you can see what megahertz those correspond to, given we're at 146.52 megahertz on the center frequency on the big spike. And so what the law says is that if your radio has to have these harmonics below 40 dB, and you can see that this doesn't pass. You can see the red line is that 40 dB line. If you remember that we're starting with 10, minus 10 to minus 50, so that's a 40 dB line in red. That means that at least two, the fourth and fifth harmonics, do not function to spec, and that's a legal radio. That radio would technically be able to interfere with people in other bands, in this case the 586 megahertz area, if they were close enough to your radio transmission. Not close enough to your radio, but close enough to your antenna, such that they would be able to interfere with their transmissions and reception. This is a Bofeng UV5R, a very popular radio. It's about $16 to $25, and this, in at least one version of it, some of the newer versions have more suppression, but typical suppression that have been seen on the market has been like this, and you can see that these radios technically operate out of spec for the FCC. So what does a good one look like? This is what a good one looks like. This is the GT5, which looks exactly like a UV5R. It just has a different designator on the front, GT-5, because its internals are different. And you can see that when it's transmitting at 146.52, all the harmonics have been suppressed. And this is what you want from any transmitter. Whenever you're on frequency, you want to see that there are no harmonics coming out of the antenna because of bad filtering in the transmitter. And so you won't find this on your test, but I just want you to understand it, because when some people are saying to you, well, I own a Bofeng UV5R, and they're saying you should buy one. The answer is it's not a bad radio. I won't complain about the radio, except this one factor is that many of them are not legal. However, the GT5, the GT-5, which is exactly like the UV5R in its functions, has better circuitry, it's newer, and it has suppression, so it is legal to operate. So you won't have to worry about it. So is it in the same price range? Absolutely. Is it the one you should choose? Well, it's the one I would recommend. And are there a lot of people using UV5Rs? Absolutely. Have there been a lot of complaints about interference with other services? Not that I know of, but is the potential there? Yes. But again, this is not a test. I just wanted you to know about it because a lot of people buy this radio as their starter radio. And if I was going to buy a starter radio today, I would buy the GT-5. Again, they have very much the same operating characteristics as far as all the features and functions. So some vocabulary about antennas: gain, the apparent increase in power, a particular direction by focusing radiation in that direction, and we measure it in decibels, as we talked about before. Isotropic is equal radiation in all directions in free space. That's that imaginary space that nothing interferes with an antenna, and isotropic means it's equal radiation in all directions. Omnidirectional antenna, there's no preferred horizontal direction. Directional antennas, they focus radiation in a specific direction. Now, what's an omnidirectional antenna? So if you took a old incandescent light bulb and you took off the lampshade and with just a free bulb in space and you turned on the power, you would see it radiated equally in all directions. That's basically the isotropic. That's basically omnidirectional. Now, what if I put a reflector, like a flashlight has, a reflector behind that incandescent light bulb? What would I get? I would get the energy being focused in one direction. And if I made that reflector tighter and tighter and tighter, the beam of that energy, the beam of that light would get smaller and smaller, but more brighter and brighter. So omnidirectional, all the energy is going out in all directions. Directional, I'm trying to focus the energy into one specific direction, and I can create a direction that's a bandwidth, or a beam width, excuse me, it's called a beam width, that is smaller and smaller depending on how I do the focusing. So that's the difference between omnidirectional and directional. So let's look at some radiation patterns. And again, you're not going to deal with this unless you get heavy into antennas. You won't be doing a lot of this, but it's something to be familiar with because if you're buying antennas, you probably see these in the specs. The azimuth pattern is this: I'm looking down from the top of the antenna, looking down at God's eye view to the antenna. The elevation pattern is when I'm looking sideways to the antenna. I'm looking from the side at the antenna. And so looking at the elevation pattern, in this case, in this kind of pattern, we're seeing we have a main lobe, a left and right main lobe, and those are the ones where we have maximum energy coming out of the antenna, and it hits that outside line. That's where we hit the maximum point, is on the outside line. We had a side lobe, which are lobes that have less energy than the main lobe coming out. We have areas where there's almost no energy, and that's called a null. And the zero line in this graph in the elevation pattern is called the ground plane. It's where the ground essentially is. So we can learn a lot from these kind of graphs. I'm not going to go into that today because that's not really part of the technician course to really digest this graph and all the things it can show and demonstrate. But just understand there's side lobes and main lobes and nulls, and that's important for you to know. And what an azimuth pattern is looking from the God's eye view at the antenna, the elevation pattern is looking at the side view of the antenna. And we can calculate a lot from this graph. Like I said, we can calculate the gain of the antenna, the beam width of the antenna, and the takeoff angle of the antenna. But those are things later for another course than the technician course. So again, we've talked about pattern of dipoles already and what they are. We have vertical and horizontal dipoles, and in free space, we can see a 3D renditioning of a model of what these antennas look like in radiation. So you're looking at a side view of this 3D rendition of the horizontal and vertical antenna. And just looking at the pattern, you can see that if we look down at the top of the antenna, that's the azimuth, we see this circular pattern. And if we were to look sideways and sort of cut this into a half and look only at half of this, remove half of the donut, so we're looking sideways into the donut, we would see these two lobes on the right side of the elevation plane in free space. And vertical, we would then see that rotated 90 degrees. Now, when you change the height of an antenna relative to the ground, then the pattern of radiation changes. So, For example, for a half-wave horizontal dipoles, that is, we have the antenna is a half-wave horizontal dipole. That's this. All these pictures here are for the same antenna, and this is what happens as we raise the antenna over what's called average ground. And you can see the radiation pattern. This is the elevation pattern. You can see as we go from 1/8 wave, we're almost omnidirectional. As we get to half wave off the ground, that is, if it's a 14 megahertz 20 meter band antenna, we're going to be about 10 meters off the ground, 30 feet off the ground, and therefore we're going to get a radiation pattern ideally like this with two lobes that have a low angle. Low angle is good for DX. And then we at 5/8 wave, we now start to develop a what's called a side lobe that goes straight up, which is good for local communications. When you have a side lobe like that, it means the energy is going up into the ionosphere and almost straight down, which is good for local communication. And we have two lobes that are good for distance communication. So as you can see, the patterns change as we go hot. We raise this antenna higher and higher. This one's specifically for HF, but you'll have some of the similar effects for VHF. However, again, VHF, most of our operation is in FM in the technician class, not so much in SSB and other things. We're vertically oriented, so we're using space wave and ground wave, not sky wave. So these patterns are really illustrating sky wave, but if it's space wave, it's really just about one thing. The higher a VHF UHF antenna goes, the better it is for line of sight. And that's the bottom line. If you're down low to the ground, obviously it's like being low to the ground trying to look at the horizon. If you go up to a mountain, you're going to see much more than you could at the ground level. And therefore, the higher you put the VHF antenna, the more it can more antennas it can receive, and the more antennas it can transmit to that can see it. So we have other antennas that are multiple element antennas, and these are good because this is one of the ways that we create a reflector behind our incandescent lamp. So if you think of the driven element, that's the center element in this illustration, as our light bulb, the reflector is the one behind it. You can see it's a little bit longer than the driven element. It's about 5% longer than the driven element. And we have a director that further focuses that beam. So the reflector basically causes the energy to be moved forward, and the driven element is the one's radiating, and its energy is being moved forward, and the director is like adding a little lens to the front of that flashlight where we can further tighten the beam down. And so the energy is being concentrated towards the front direction. By the way, this is called a 3-element Yagi antenna, Y-A-G-I. This is actually an illustration of one called a tape measure antenna, where you take a metal tape measure and you cut it up to make this antenna, and it's on a PVC boom. And you can see where the feed point is, then the coax transmission coil that's coiled up there. So a reflector, again, is a passive element. There's no electricity coming through it directly. We're not putting transmission line to it. It's all dealing with energy that's reflected from it, from the driven element. And the driven element is where the transmission energy is applied. The director focuses the energy forward. So the reflector basically reduces the energy going backwards behind the driven element and forces it forward, and the director further focuses it. And the elements that are not the director, that is, not the driven element, so the reflector and director, because they're not attached to any wires to the radio, they're called parasitic elements. The driven element is attached to the radio so that it is an active element. The reflector and director are passive elements. You can always have one reflector and one driven element. That's a 2-element Yagi, or 2-element beam. I have a VHF antenna that is a 15-element antenna. It has a driven element, one reflector, and has 13 directors. It's about 15 feet long when it's in the air, and you can imagine that concentrates the energy into a tighter and tighter beam. It means it's more directional, but it allows the antenna to focus the energy so I have more range. And so here is that azimuth pattern for this antenna, and you can see we have a main lobe going to the right. We have a couple of small lobes to the back of the antenna, and they're very small compared to the main lobe. So this antenna has moved a lot of the energy to the front as we're facing it. And so and if you look at the free space gain of this antenna is 8.47 dBi. We know that dBi means isotropic antenna. So we know that it's 8.47 better than a isotropic vertical omnidirectional antenna. And if we were to measure the gain from the front of the antenna to the back of the antenna, we can see the energy concentration is 28 dBs, 28 decibels of energy gain. Again, we didn't put any new energy into this. We haven't created new energy. It's still the same energy coming out of the transmitter. The difference is like we put like a light bulb with a reflector behind it. We've concentrated that energy into the one space, into a narrow space, so that in that one space it's going to be very bright compared to if it was omnidirectional. And again, what we talked about before, there's a main lobe and there's some nulls and some side lobes, as you can see, the smaller ones on this pattern. Other antennas, we have quarter wave vertical antennas. And they're very common omnidirectional antenna for VHF and UHF. You can design them for whatever frequency you want using the formulas we just gave. Very easy to construct these antennas. And it has a quarter wave ground plane. Now, in the picture we have here, this ground plane is basically 4 wires that are aimed downwards. And in this configuration, when you have elevated ground plane, they're called counterpoises or counterpoise. And if they were on the ground, that is, if we had the antenna laying on the ground where these wires were laying on the ground and the vertical was coming out of the top, out of the ground, so to speak, then we'd call these radials. And their function is the other half of the antenna. So that's what we're basically doing, is the vertical is one side of the antenna and the ground plane is the other side of the antenna. And we use a certain number of antennas, wires in the ground plane or more than the vertical because we're creating a field path to help return the energy back to the coax down the transmitter. Remember, we're sending energy out, and then of course we're getting energy back on the return side. So this is a quarter wave vertical, and if we were to make these horizontal, we would get, let's say, an impedance of 35 ohms. And as we bend these further and further into vertical, so that the antenna becomes a straightened up and down vertical, then the impedance moves towards 50 ohms. So how we bend these radials, these counterpoises, determines what the impedance of the antenna is, as well as the height of the antenna above ground. This is another common antenna. This is a J-pole antenna. Can be built for 2 meters, or it can be built as dual band, 2 meter and UHF. A very common antenna. They're very popular. They're generally made out of a copper pipe, but you see on the far right, you can also make them out of a thing called window line, and they can be rolled up and put in your backpack and used when camping or in doing other things. So if you need to extend the range of your HT, it's a great way to extend your range of your HT because it's giving you a better antenna than the one in your HT, and you can throw it up in a tree and tie it up and attach your HT and have much more range than you would with your regular antenna. So it's a nice antenna to have around when you're operating portable, or you're carrying it when you're camping or backpacking and things like that. Because if you need to be able to reach a repeater and your smaller antenna on your handy-talkie cannot do the job, you can basically pull this out, unroll it, throw a rope up onto a tree and hoist it up, and you have much better range and ability to be heard. So as we're closing for tonight, we're going to do feed lines. This won't take as long as we've covered so far. I know there's been a lot of technical information, a lot less calculation, but a lot more information, I guess, in some respects. Again, remember, the book is the source for how much you need to go deep into this, and always be working the question pool so you become familiar with what's being asked. And if you have any difficulty with anything, of course, email me, and I'll be happy to help you. Let's talk about feed lines, which is how we're going to move the energy from the transmitter or transceiver to the antenna. So, as I said, they move the energy from point A to point B, from transmitter to the antenna, and back, and also from the antenna to the transmitter. And the basic feed lines are a coax cable and open wire line, which is also called ladder line or window line. And you can have power losses that occur in the feed lines, and the losses usually increase with frequency. And so, as we've talked about before, you can have a feed point, and there's a coax line or some wire feed point, and we may have to do an impedance transformation so that it matches the 50 ohms of the transmitter. And so we have an optional impedance matching unit there, which could be an antenna tuner, which we'll talk about, or it could be that impedance transformer that we talked about. And then we have coax or transmission line that goes to the radio. So coax is the most common feed line that we see around today. and it generally is 50 or 75 ohms is available. It will accept various types of connectors. Some types are designed to be buried, and they may have an air or solid core. And this is how, and you can see the diagram of how they're described here above. They have a center conductor, a dielectric or insulator, an outer conductor or braid, and then a heavy shield, a heavy outer jacket, excuse me. And you can see the picture below. We see the center conductor below. You know, the white is a plastic kind of dielectric or insulator. Then we have a single shield or aluminum foil that's wrapped around that. And then we have the outer conductor or braid, then followed by the black heavy-duty jacket that protects the wire. And this is very common, and we have connectors that connect to this, and we have special tools to help us put these on and seal them up. And again, they're very popular. They're easy to work with. They're very forgiving in the sense that you can run them anywhere you want for all intents and purposes, including bury them. You just have to protect and make sure that they're sealed from water. That's the main thing, is to be sealed from water. We have different connectors that we use on these wires. We can use UHF connectors, very popular in most of your HF transceivers, is what are called UHF connectors, otherwise known as 259s. We have BNC extension connectors. This says extension cables. It should just be BNC connectors. It happens the way the picture I pulled from a catalog. We have N-type connectors, and again, each connector has a different purpose. N-type connectors are actually superior to UHF connectors, but not so often used in amateur radio. And we have SMA-type connectors, which are very much used in your HTs. So most of your handy-talkies have SMA-type connectors. And if you want to attach those handy-talkies to external antennas that use UHF connectors, then you have a special adapter that screws into the SMA and then gives the coax a UHF connector to screw into. Now, coax wire comes with power losses. And so you want to choose coax that will give you the least amount of losses for the number of feet of the transmission line. So if you just have an antenna that's 10 feet away from you, you don't really need to worry a lot about losses in the UHF and VHF ranges. That's the 144 megahertz and 440 megahertz area I have in red here. So even though the losses are very high for, let's say, RG58, in those frames, it's per 100 feet. So if I were only going to have 10 feet, well, then it would be a lot less loss, and it might be, you know, acceptable. So in my case, at home, I have about 75-foot run to my antenna. So therefore, I chose, based on what I could afford, to have LMR 400, which is a low-loss coax cable at that range. I do a lot of HF work, so you can look up to the 7 megahertz, 3.5, 14 megahertz, 28 megahertz areas, and you can see it's got a lot of low loss, which means I'm not losing as much power in dB to the transmission line. And so therefore, I prefer that kind of cable. I want to get the most amount of power to my antenna as I can. Again, if it's a more expensive cable. Could you use a cheaper cable? Absolutely. If you had a shorter run, would you use a cheaper cable? Absolutely, you could do that. So it all depends on what your trade-off is on what you want to do. But the thing to keep in mind is coax losses increase significantly when you get up in the VHF, UHF area, so you want to keep those transmission lines as short as possible. Choose them to make sure that you have the whatever least amount of loss you can afford. And that's important because when you think about it, a 4.2 dB loss at 100 feet, so that would be RGX, if you go at RG 8X at 144 megahertz, you'll see it's 4.22, can't talk, 4.2 dB loss over 100 feet. And at 144 megahertz, if you had 100 feet of this cable attached to your antenna, result in about 20 watts getting to your antenna from a 50-watt transmitter. Now, that may not bother you because of what kind of work you're doing. However, if you're trying to do long-distance work, you want to get more of that power to the antenna, so you might choose a different cable. So just keep in mind that coax cable is easy to work with. You can run it in a lot of different forgiving ways, but it does carry a loss, and the loss increases with frequency. We have open wire line, which are ladder or window lines, and we have what's called 300 ohm twin lead, which, as you can see, is in the picture, two wires running parallel to each other with a polyethylene insulator in between them. You also can have 450 ohm window line, which you called it window line because there's windows in the insulation between the two wires. However, you can also get 300 ohm open window line as well. So the 300 ohm twin lead is one version. You can get 450 or 300 ohm window line. And the far right is what's called 600 ohm ladder line. And what this is literally someone has drilled holes in dowels or in PVC. It's an insulator, and they're about 6 inches to 12 inches wide, and it forms a ladder. And you have a single wire on one side and a single wire on the other, and it comes down, and that's about 600 ohm ladder line. Why are these good? Well, they can be less expensive than coax. They have much lower losses than coax does. However, they're more difficult to use, and they also have higher impedance. And if you have higher impedance, it means we have to do some type of impedance transformation to get them down to 50 ohms so we can use our 50 ohm transmitters with them. What makes them more difficult to use is that certain of these lines have to run a certain distance from metal. Window line, for example, has to have a certain number of twists in the line to help it reduce the stress on the window line. So you don't see it used very often. Oftentimes that roll-up J-pole was a window line. And window lines can be used as part of an antenna for transmission impedance line matching as well, which we'll be leaving for the general course. But just keep in mind you can use these. They're effective. They have less losses, but they can be a little bit more difficult to use. Okay, as we finish up, we're going to go to standing wave ratio. And when the feed point and feed line impedances don't match, and we've talked a lot about that, some of the RF power is reflected towards the transmitter. So what happens is we're pushing energy up to the antenna, and if the impedance doesn't match sufficiently, then some of the energy is going to basically bounce back down off the antenna back towards the transmitter. And it's going to go back up and down, up and down. It's going to basically, eventually, through losses in the system, it's going to dissipate. And this is called the standing wave, the standing wave ratio. So again, the original signal is going in the blue is going out towards the antenna. If we have impedance mismatch, some of it's bouncing back out of phase with the original signal, and you can see the reflected wave is the summation of that that's coming back down the wire that we're measuring. And so the forward power is what comes out of the transmitter, as I just said. The reflective power is what's coming back down from the antenna when the impedances don't match. And the SWR is the ratio of the standing wave max to the min, or forward to reflected power, and that's the SWR ratio. And when we're trying to design an antenna system, a transmission system, we want to get that standing wave ratio as close to 1-to-1 as possible. Is it okay to be off 1-to-1? Absolutely. 1-to-2, 1-to-3, not so bad. The power losses are not significant enough that we're worried about them when we're dealing with most power situations like 100 watts. If you're down into the 5-watt range and you want to be a little bit tighter with the SWR because the losses can be more significant in the sense that you have a 5-watt transmitter, you lost a watt in losses. That is 1/5 of your power gone, versus you've lost 1 watt and 100 watts, and that's only 10% of your power. So just keep that in mind, is that when you have lower power, these losses can be more significant. And the higher SWR means more feed line losses in general. It can also mean that you have a bigger mismatch between the antenna's impedance and the radio's impedance. So there's different sources for high SWR, including you have broken connectors, you have corroded cables and things like that. And we measure this with an SWR meter or SWR bridge or antenna analyzer. The ideal ratio is 1-to-1. Anything under 2-to-1 is generally considered fine. The losses are acceptable. Most antenna designs specify bandwidth given the center frequency plus or minus 1.5 to 1. So generally speaking, when we look at the bandwidth of an antenna, we look at it from the point of view of the 1.5 to 1 to 1.5 to 1. So if you think of the center frequency of, let's say, 14.2, and we saw the SWR was 1.5 at 14.1, and it was 1.5 at 14.25, that we would consider the bandwidth of that antenna is 14.1 to 14.25 with a center frequency of 14.2, because we're using that as our designation as bandwidth for most cases. And anything below 2.1 is generally the transmitter can compensate for, and if it gets higher than 3.1, most transmitters will begin to have circuitry. They have circuitry in them. They'll begin reducing power to protect the transmitter if they see a high SWR. So, and when we're fixing SWR issues, we generally, as I said, we use impedance transformation either, or we use the L or T networks that I described in the earlier slide. So we ensure all the connectors are in good working order to fix SWR issues. We confirm there are no breaks or corrosion in the feed line or antenna. For new antennas, we make sure we trim them to length using an antenna analyzer SWR bridge, and we use an impedance transformer and or an antenna tuner to match the impedances when there's an impedance mismatch. Now, remember one thing. Antenna tuners don't tune antennas. Remember, an antenna is got one resonant frequency. There's nothing you can do about that other than to change the physical characteristics of the antenna. So we have this thing called an antenna tuner. It wasn't originally called an antenna tuner. It was called an antenna transmatch. And for some reason, somewhere along the line, that it got turned to called an antenna tuner. It doesn't tune the antenna. It's doing impedance transformation. So we have a 4-to-1 transformer that's in the bottom there in the box with the blue wires and the black wires. And then we have at the top a manual antenna tuner. And what you do is you manually adjust that inductor and capacitor. And you have two needles, one for forward power and one for reflected power. And when you in that little meter on the left side of the manual tuner in the white box, and when the needles match together, it tells you on the red line what the SWR is, and you adjust those dials until the SWR is at minimum. And then below, we see the inside of an automatic antenna tuner. We have a series of coils, that's inductors, and a series of capacitors, and a series of relays. And there's a computer that controls this. And when you push a button, the computer goes through various combinations of capacitors and inductors to find the one that will give you the impedance transformation you need. So there's three different types. One's passive, the 4-to-1 transformer, in this case the impedance transformer. This happens to be 4-to-1. The other is manual antenna tuner or manual transmatch, and then an automatic antenna tuner or an automatic transmatch. All three are in use, and sometimes you use a combination of two of these. Two of them specifically being the transformer and either a manual or a transformer and an automatic tuner.